Okay, so I'm going to start now, even though people are still coming in. So my name is Louis, I work for Amazon, and we're going to be talking about runtime polymorphism today. And we're going to start right away because I have something like 80 slides in just an hour. So, all right, so as a short refresher, I expect that actually most of you know what runtime polymorphism is, but let's get a small refresher. So imagine you have a set of types, and they're all related by their interface in some way, right? And then you want to return them from a function based on some runtime condition, for example, or in this case, some user input. So I don't know exactly what type I'm going to be returning. In this case, I need some kind of, I can only return one type from the function, so I need some kind of erasure to coerce all these types into a single type. Or if I want to store objects of these different types in a container, for example, I need a single type to basically represent all of these types. So I'm going to need some kind of runtime polymorphism there. And sometimes variant does the trick, right? Sometimes it's enough, but it only works when you have a closed set of types, and when you know all of your types in advance, when you can name them, when it's convenient to name them. Which is not always the case, right? And it's also not always convenient to use a visitation-based approach. So when that's not the case, when you have an open set of types, you want to use runtime polymorphism as we usually understand it. And obviously, C++ is a solution for that. We all know what it is. It's called inheritance. And the way it works, essentially, is that you have a base class, which defines the interface, and then you have derived classes, which derive from that base class. And they implement this interface in different ways. And they can have different representations. Like I could have different members in my derived classes and so on. Under the hood, what this looks like is basically you have a pointer, because usually we're going to manipulate these derived classes using a pointer to the base class. So you have a pointer which points to an object of a derived type, and then within that object, there is a pointer to a vtable. And the vtable contains function pointers that are the most derived implementations for the interface that you defined in your base class. Okay? I hope everybody's following me at this point. So this is typically how you do it in C++. But it has a bunch of problems. And that's not the goal of this talk. Is not to rant on inheritance. That's not the goal, but to act as like a motivation for what we're going to do next. I'm still going to go over a few of them. So first of all, it bakes in reference semantics. In C++, we're really loving of value semantics. But when you start using inheritance, because you need to use a pointer to the base class, basically you lose that ability. And for example, if I make a copy of a pointer, I'm not making an actual copy of the object it's pointing to. So now I don't have two disjoint objects. And that's just really difficult. It makes it really difficult to do local reasoning, for example. It also causes you to do heap allocations because you got to store these objects somewhere. And so you're usually going to put them on the heap. And that's costly. It also bakes in nullable semantics. You just wanted to have polymorphism, and what you end up with is having to manipulate pointers. A pointer can be null, and now you kind of have to check for null, or at least you're living with that additional state in your object now. Because you have resources, you need to manage them. And so you have to pick one of our really nice, smart, or not so smart pointers in C++ and decide how you're going to, what's the ownership of this object like. And here I'm saying like unique pointer, but really we're all kind of lazy and we all end up using shared pointer, right? And that's even more costly. And if we use raw pointers, then it's complete hell. Because whoever gets that pointer needs to know that needs to not forget to delete it. It also doesn't play really well with the standard algorithms. Because, for example, if I want to sort my vector of vehicles, here it's not really going to do what I want. It's just going to sort the vector itself. These are pointers. These are not the actual objects. So it's going to sort them by their address, which is obviously not what I wanted. So everything becomes a little more complicated when you start using pointers to indirect through everything. It's also intrusive. If I have a third-party library or like a fundamental type or something, and I want it to satisfy my interface, or if it satisfies my interface, I have no way of doing this with inheritance because I would need to reopen the type and add a base class to it. And that's very intrusive, so I can't do that. So anyway, the point of this talk is not to discuss the drawbacks of inheritance. Sean Parent does it much, much better than I do. So I encourage all of you to watch this talk. This talk is the Runtime Polymorphism talk in his Better Code series. But there's other talks that from Sean that treat this subject. By the way, I think this is one of the best talks I've seen in my life. So, okay. I find it really sad that C++ only gives us inheritance to achieve runtime polymorphism, because what I wanted is this, essentially, okay? And this has nothing to do with the interface keyword or the interface meta class that Herb talked about yesterday, just to set the record straight. So imagine I have this imaginary interface thing which creates a vehicle. It just describes the interface that I want, okay? And then I have a bunch of types that satisfies this interface. Obviously, they do satisfy the interface. They don't need to have any base class or anything. They just need to satisfy the interface. And then I could, for example, create a vehicle, a vector of those, and when I push back or when I insert my things that satisfy the interface, it makes a copy of them, and we're back in value semantics world, right? We're actually manipulating values. I mean, we have no way of achieving this right now in C++, maybe, but just imagine at this point. I think this would be much closer to what we want. Like no issues with ownership, with memory management, with nothing. All we have is types that know nothing about inheritance, and we can use them polymorphically. That's neat. So this talk is going to be about how we can achieve this. The whole talk is only going to be about different ways of implementing this imaginary interface keyword, or rather the imaginary vehicle type that it generates. This is the only thing we're going to do. And so with inheritance, like I said, you basically have a pointer to a derived type, and then you have a pointer to a vtable in there. So to give you an idea of what we're going to do, we're going to play around with, what if I take the vtable, for example, and I pull it down one level, and I bring it like into the yellow box there? Or what if I try to inline this in there? Or what if I try to move these boxes around? What does that give us? Does that even make sense? And so that's exactly, we're going to be exploring different ways of organizing these boxes. And I'm going to steer the discussion in one specific direction. I'm going to try to treat the storage, which is this green box here, and the vtable, or the dynamic dispatch, which is this purple box here. I'm going to try to treat them independently. And so we're going to find a few ways to do the green box, and we're going to find a few ways to do the dynamic dispatch, the purple box. And if they're really independent, we're going to be able to mix and match them, which gives us some nice, flexibility. All right. So first one. If our vehicle, let's say we just try to pull down the vtable one level, okay? So imagine the vehicle type, the magic vehicle type, is not just a pointer anymore. It actually has it's actually a pointer to a vtable, and yeah, go ahead. So the question is whether I can point with the mouse cursor. It's going to be really difficult because there's some lag. There's some lag with the mouse there. I understand that, yeah. But this is why you guys are here and they're not there. So I'm just going to waste a bunch of time otherwise. So So the idea is, what if you pull the vtable down, right, into the vehicle itself? So the vehicle now has a pointer to vtable and a pointer to the actual object. Okay. So let's see how we can implement that. So here I have my vehicle, which has a pointer to a vtable, and I'm going to show you how the vtable is implemented. Okay, there is a type called vtable there. I'm going to show you on the next slide. So I have a pointer to a vtable, and I have a void pointer, which is basically a pointer to whatever I'm holding, whatever the vehicle is holding. All right. I can't make it a pointer to a base class because there's just no concept of a base class in this approach. And then I have a constructor that can be constructed from anything, because that's what I want. I want my vehicle to be constructible from anything that satisfies my interface. So the way you do that is you have a templated constructor. And I would have some fancy enable if business here to say, only enable this constructor when you have an accelerate method in this case. And I'm skipping a bunch of details because this is slide code. So I have a constructor that can be constructed from anything that's a vehicle, and then imagine that I have a vtable somewhere. I initialize my vpointer from that, which is what the compiler does under the hood, really. And then I copy my vehicle. I copy, like, let's say the car or the truck or the whatever it is, and I keep my pointer to it. And I'm also going to skip for all the talk, I'm not going to show the copy constructor implementations. There's already enough stuff to cover, but they're easy to implement. And then when I want to call my method, I just go in my vtable by going through my vpointer, right? And then I call that on my this, which is basically the pointer to the object that I'm holding. And when I destroy my vehicle, I just go I indirect through my vtable again, and I go destroy the thing that I'm holding. So I hope this doesn't look too weird to anyone. Now let me show you how the vtable looks like. So I have a vtable. A vtable is just a struct with function pointers. It's just a table with function pointers, right? And so I have function pointers in there. And then I need to initialize my vtable somewhere. So what I do here is I have this little, this is a variable template. This is a C++14 variable template. And basically what I'm doing is I'm creating an instance of this vtable for any type t. And the way I do that, I initialize it with lambdas, which will, because they're stateless lambdas, they're going to decay to a function pointer. Okay, so I'm just creating functions here inline. And I take in a void pointer this, but I know I'm the vtable for t. So I know this is actually a t star. So I can static cast it to a t pointer, and then I do the static dispatch. I call my accelerate method in there. Right? And since this is static dispatch, the compiler is going to see this and is going to be free to do any inlining it wants. So this should be basically considered equivalent, absolutely equivalent to just calling accelerate directly. And so for the delete here, I'm just static casting to a t star, and then I'm deleting the object. Okay? So I'm just going to go back real quick here. So again, you have the vehicle, it gets constructed from anything, then you initialize it with the right vtable. So that's a table with two function pointers in there that have been initialized in the next slide. And then I make a copy of whatever I'm containing. Is anybody completely lost at this point? Okay, that's really good. Okay. So I wrote this little library, and the purpose of this talk is not to talk about the library, but I'm going to show snapshots of how I'm going to show the equivalent using the library every time. So it gives you like a poly type basically, which handles much of the nastiness under the hood, and essentially what I want to point you to is it accepts what I call a storage policy. So it's a way of like storing the underlying object. And here we're just using the remote storage policy. And that's basically equivalent to what we implemented by hand here. Okay? And then when I want to dispatch my vehicle, when I call accelerate, it's going to reach into the vtable of the poly to the accelerate function, the function that's that matches the accelerate string. And then it's going to call that on the poly. And now you're looking at me and you're like, are you crazy? You're replacing virtual functions by like a map lookup or something? Well, so if you don't know me, I'm a crazy metaprogrammer. And this is a compile time string. So this whole expression here is completely resolved at compile time. And that's equivalent to doing a struct, accessing a member in a struct. So these are absolutely equivalent. And it's not only in theory, like, you know, I'm benchmarking, and it's exactly the same as doing the handwritten implementation. But that's not so important. The really important part is there's a Dino remote storage thing which makes it equivalent to what we wrote in the previous slide. Now I do need to specify what the interface is. So I have this fancy way of creating vtables, okay? And basically I'm creating a vtable saying, hey, you're gonna need to be copy constructibles, or there's gonna be a copy constructor in the vtable. You need to be destructible, and you need to have this accelerate function, which has this signature. And then I fill my vtable, I say, here's how you implement accelerate. And I'm not getting into any details there. It's just to show you, like, basically, you know, if you're interested, go read the documentation, but basically, I have a way of defining my vtable. And so the strength and weaknesses, not of Dino, but of the approach that we just looked at, okay, which is to basically pull the vtable down just one layer, it's a simple model. It's still very similar to classic inheritance. So it's easy to reason about if you're used to reasoning about inheritance. But it always requires a heap allocation because we're still going through a pointer. So that's not really ideal. So we're going to look at a different way of implementing this. What if we did this instead? And that's called the small buffer optimization, SBO for short. So the idea behind SBO is basically that you have a pointer. You either have a pointer to the heap, or you have a local buffer of a fixed size right there in the vehicle, in the object, right? And if what you're being constructed from, so like the derived class in a sense, if what you're being constructed from fits in the buffer, you can put it there, and you don't need to go to the heap because you have enough storage right here. And if it's too large, then you need to go to the heap. And there's a bunch of ways of implementing this. But you basically need one bit of information encoded somewhere, somehow, to know whether you're on the heap or in the local buffer, okay? And the vtable here, that doesn't change from the previous approach. Like, we're not gonna touch vtables for a while now. You still have a vpointer, whatever. And so one way is you just have a bool there. That's a way of doing this. And then, yeah, this pointer here basically points either on the heap or it's not used because it's in a union and the buffer is used instead. And the way we can implement this is basically you have a vpointer, the union, with some aligned storage. And then when you get constructed from any concrete type, you check, oh, do you fit in the buffer? In my case, I have 16 bytes. So if the size of the concrete type that I'm being constructed from fits in the buffer, or doesn't fit in the buffer rather, if it's too large for the buffer, I put it on the heap. And otherwise, I'm gonna placement new it in my buffer. And a placement new is a form of a new expression that basically just constructs an object of a given type. It basically calls a constructor on a piece of memory. And a piece of the address in memory where I'm constructing my object is $buffer here. So I'm just constructing, at the location of the buffer, I'm constructing an object of type any. And then when I want to call a function, I just go through my vtable again, and if I'm on the heap, I use my pointer. Otherwise, I use my buffer. Is anybody completely lost? All right. There's a bunch of implementations, like I said. I just showed a very naive one. Another way of doing this is that you can put the bool, actually, instead of in the object, you can put it in the vtable because there is one vtable per type, and so each vtable kind of knows whether the type that it's being that it's useful for will fit in 16 bytes or not. So that's a way. You can actually inline that knowledge in the functions that you put in the vtable as well. So they're going to receive a vehicle, and they're going to know whether they should reach into the small buffer or on the heap, right? So that's a way of doing this. Another way of doing this, thanks to Gasper, I stole it from him. And basically is you have you always have a pointer. Instead of having a bool, you always have a pointer. And the pointer is either pointing on the heap or it's pointing to a local buffer. And so you don't have a bool, you don't need to branch every time that you're gonna access your storage. You just follow that pointer wherever it leads you. And it might lead you just to the local buffer right after, or actually on the heap, yeah. But the question is, but you still need to know whether it's on the heap. Yeah, you do. You just follow the pointer. The pointer has been set up to be either pointing to the heap where the thing lives, or on the. Okay, I understand your question now. Yeah, okay, you can actually retrieve that bool, that bit of information, to know like whether you should free the object you're pointing to or not by saying, does my pointer point to right after itself? So that's how you can retrieve that bool. And so with Dino. You just need to use a different storage policy, SBO storage with whatever size you want. That's the only line that changes. So the strengths and weaknesses of this approach is that it does not always require allocating, so that's good. But it takes up more space, and copy, move, and swap operations are kind of complicated. You have to handle a bunch of different cases, like if this guy's on the heap, that guy's on the stack, and so on, right? So you have I think 4 combinations to handle. And dispatching may also be more costly depending on how you actually implement it. All right. So we're going to, do I have any questions at this point? Yeah.
So if you go back, can you go back a couple slides, please?
How many?
Stop. No, there. Nope. Back one. There. So have you considered, instead of storing the bool in the vtable, just store the size of the object in the vtable, and then you can have different small buffer sizes optimizations, and the test is not is the bool on heap, but rather is the size of the buffer.
That's a good point. So in Dino, I actually do store the size, but I had not thought about using it for that purpose. I think that's an interesting point. But I think the more interesting thing you can do here is really inline the knowledge of whether the bool is true or false. You inline that in the vtable, in the implementations of the functions in the vtable. But yeah, that's a good point. That's another implementation. So you have all kinds of ways of encoding that bit of information. And actually, there's another thing you could do. You could also it's crazy, but you could encode that bit of information in the low bits of your vtable pointer, because you know the alignment of your vtable pointer. So you could do some bit twiddling.
The goal I was shooting for here is not necessarily just a different kind of, different buffer sizes, but also to get back to the idea that with inheritance-based polymorphism, the vtable is constant. It doesn't change at runtime. And I'm wondering if you can get back to that.
That vtable doesn't change, never changes.
Right, but if you had different buffer sizes policies, then the on heap would have to change. Sure.
So you would, yes, that's true. You would need to create one vtable per such buffer size. Yeah. So that's an interesting. There are probably many other ways of implementing this that I haven't thought about. But this is just a general idea. You can have a local buffer and have a fallback to the heap. And what we're going to do now is we're actually going to push this further. We're going to say let's not have a fallback. So you have a local buffer of a fixed size, and you don't have a fallback. So when the type is too large, it doesn't compile. That's what you want. The question is, who deletes the vtable? The vtable is in static storage. Nobody deletes it. No, static storage. Not thread local storage. Static storage. It's const. Actually, it can be const expr even. No need to do anything with it. So if it doesn't fit in the local storage here, the only thing we can do is really fail to compile. Okay? And the way we can do that is, we just have some buffer of a fixed size, align storage 64 bytes in this case, for example. And then when I get constructed from any concrete type, I make sure that it fits in the buffer, right? So if the size is less than or equal to the size of my buffer, and here I'm skipping some alignment checks and so on, but it's not good. So if it doesn't fit in the buffer, then I basically give a compiler error. And otherwise, I placement new it in the buffer, and that's it. And then when I want to call a method on it, I just go through my vtable. I always need to go through my vtable, and then I call that, and my this pointer is basically the starting address of my buffer. And then I need my destructor. I call my destructor. I don't need to free anything here. I just call my destructor on the buffer. And with the library, you just have to say local storage and then pick your size. So the strengths and weaknesses of this approach are that, well, the main strength really is that there's no allocation ever. And you're guaranteed to never get an allocation, right? You'll never get one. The dispatching is as simple as it gets because you always just go reach to your buffer, which is right there. Actually, if you have the object, the buffer may already be like, on the same cache line or something. So this is as simple as it gets. But it does take up more space unless you have many objects that have basically the same size and they all have the exact size of the local buffer, in which case you're using your local buffer size optimally. But in some cases, it can result in some wasted space. Do I have any questions at this point? Is everybody following me? Yeah.
I think this is all. Would you have like different types for the same conceptual type, like different based on the storage policy?
Could you have different? The question I think is, could you have different types for the same, representing like the same vehicle for interface, but having different storage policies? Absolutely, depending on how you use them. Why not? Right? You'd have to make them interoperable, but probably. But if you're using vehicles in a certain way in your application here and a different way there, it makes total sense. Or maybe like you have different vehicles. They're larger, they're smaller. It makes total sense to tweak, your implementation of polymorphism to your use case. That's what I think. Yeah, and it's tedious if you do it by hand. If you use a library and you could templatize your vehicle class on the storage policy, and then you just have to change the storage policy that you're using. It's really easy. Okay, so let's look at a few benchmarks. These are like super micro. Okay, these are really micro benchmarks. So we're not going to draw any firm conclusions from them. We're just going to draw some really coarse-grained conclusions from them. Okay, because I don't want to get into that, and then next thing you know, a compiler engineer comes to me and says like, this is you're full of crap and blah blah blah. So I realized that the columns are maybe not visible from the back. I'm sorry for that. So anyway, this benchmark shows creating many 16 bytes objects. And I'm going to go from the left to your left. The leftmost one is inheritance. Basically, I'm going to the heap there. I'm allocating. And all that this graph shows is that you're doing an allocation and you're paying for it. Okay. Remote storage, next. Also, there's an allocation. They're in the same ballpark. SBO storage with 4 bytes. The third one is the SBO storage with 4 bytes. 4 bytes is not enough to store 16, so I'm always going to the heap. I can never actually put the object in my buffer. And so I need to go to the heap, and, well, I pay for it. Same for 8 bytes, which is the next one. And then when it drops, it's the SBO storage 16 bytes, where suddenly my objects fit in my buffer. I don't have to do an allocation, and boom, the cost drops dramatically. And the last one is the local storage with 16 bytes, where the object always fits as well, so I'm not paying for an allocation. Yeah.
Have you tried this with a pool allocator instead?
Have I tried this with a pool allocator? No, I have not. That's a good point. This is just standard allocator. But regardless, I doubt that you can find anything faster than just stack. Yeah.
How many types did you use for this benchmark?
Can you repeat that?
How many types of objects did you use for this benchmark?
So I'm using Google Benchmark, basically, and I'm using Google Benchmark, which iterates until the variance of the measurements goes really small.
How many classes there were?
Oh, how many?
It's like each class is a virtual jump to another place.
There's only one class here. I'm just creating I'm just creating it's basically an aligned storage of 16 bytes that I'm erasing in my object, right? So it's really naive. The only thing I want to show here is that, hey, you need to pay for an allocation. This is not like an exact number or whatever, but like surely allocating is going to be a little more costly than not allocating, right? And that's what this benchmark shows. This is like how coarse I want our conclusions to be. Okay, now I'm accessing many 4 bytes objects. I have like 10 times 3 virtual method calls, and then Google Benchmarks iterates this until the variance of measurements it looks satisfactory. Basically, I'm not drawing any conclusions except that they're all in the same ballpark. Okay, so I'm not trying to draw any conclusions except to say that, well, probably the speed of dispatching may or may not be an issue. Like in your application, you should just measure that. So, but the guidelines are, you should try to use local storage whenever you can afford it, whenever it's convenient for you to use that, because you're always going to get rid of the allocation, which we saw actually mattered, right? Otherwise, you should try to use the small buffer optimization with the largest possible size, or largest reasonable size. And you should go to a purely remote storage only when you know that like your sizes are so sparsely distributed that you're rarely going to take advantage of a small buffer optimization, and you're always going to be wasting the space, right? And actually, before this, should be just measure it, really. Like, obviously, just measure it. Don't take any advice blindly. But otherwise, I think these are the most reasonable, after measuring, these are, I think, the most reasonable guidelines I was able to come up with. Okay. Now we're going to leave the realm of value semantics for a second. So we're going to look at non-owning storage. What I want is to have basically a polymorphic view over some existing object. And I don't want to own it. I'm not making a copy. Okay? So the way you can implement that is by simply having you still have your v pointer, and then you have a non-owning, you have basically a void pointer, but this is not owning. So you just have a reference essentially to the actual object that lives somewhere else. So in this case here, for example, I have my truck, it lives on the stack, and then I call my process function, which takes a vehicle, but there's no copy being made because I don't actually try to do the object. I just take the address basically of my object under the hood. Right? And there's nothing to do in the destructor as well. Yeah. You have to speak up. How is it different than passing it as a vehicle reference? No. So if you pass it as a vehicle reference, in order to get a vehicle, with the value semantics-based approaches, you're going to create a vehicle which may incur an allocation, and then you're going to pass a reference to that. It's not what you want. What you want here is just to pass basically the truck itself. And what you want basically is just to bind a vtable of your choice to that reference. No, in this case, truck doesn't know anything about vehicle. That's right. That's the point. It only has the right interface, so that when you create the vehicle with the non-owning storage, you're creating a vtable from that, right? And that's what binds to the accelerate method of the truck.
But you could achieve the same effect by just making process a template, right?
Well, yes, but this is slide code. So it's not always the case, right? If you had, first of all, it's not always possible, and it's also not always convenient. Let's say you want to have a fixed API and have it be extensible by other other clients without you having to know what their types are going to be in beforehand. Okay. Any more questions on this? I'm not going to show the implementation because I don't want to run out of time. Okay. So another thing you can do, and now we're actually back in the value semantics world. Another thing you can do is have shared remote storage. And this is something that Sean Parent talks about in his talks. Basically what you do, the idea behind that is you use a shared pointer, okay, so that all the vehicles share the same underlying representation, okay? And so when you make a copy, you're only creating a new shared pointer to the original one. And so that allows you to do optimal sharing. Now, when you want to modify one of these vehicles, that's when you actually make a deep copy, and then you modify it. So that's copy on write. So that's an interesting way of retaining value semantics whilst making it easier to do optimal sharing and not having to worry basically about breaking value semantics. And I'm also not gonna show the implementation for the sake of time. Any questions? I know this is kind of since I'm not showing an example, it may be hard to picture it in your head. So go ahead if you have a question. Okay. So now it's not clear though why we care about all of this actually, right? So I'm going to try to convince you that we care about this. So have you heard about standard function? Probably. Who has? Great. So standard function is basically is a type. You give it a signature, and then you can stick any function that satisfies that signature, including function objects, and they can be stateful. Okay. You can stick anything in there, and it's going to have your call operator, and it's going to call the underlying function. In-place function is something that was proposed to SG14. Actually, we discussed that yesterday. And the idea is it's like a standard function, but it never allocates because it has a fixed size buffer. Have we talked about that? And function view is something that Vittorio Romeo blogged about, and there might be a proposal baking, I don't know. But the idea is basically it's like a stud function, but it's like, well, it's the equivalent of string view for a standard function. So it's like a non-owning standard function. So you just take a function view, and you're not making any copy, but you can pass anything that's callable with the right signature, okay? And so what if we did this? So imagine I have a basic function, much like basic string, same idea, a little bit. I have a basic function, which has a signature and some storage policy. And then I do this little dance here. I can be constructed from anything. I should, restrict this with some enable for it to, really work. And then I just create my poly under the hood, which does all these nasty tricks that we've done manually for, in the previous slides. And then I have my call operator, which just dispatches to the virtual, to the vtable and calls it with the arguments. I should be doing perfect forwarding as well. I'm trying to save some trouble here. And then imagine I have this callable interface, which I'm not going to show, but you define it. It's not too difficult to define. It's this little boilerplate that I showed before. So you define your callable interface, and then you just set the storage policy of the dyno, of the poly. Imagine we have this. Then here's all of these three proposals, and actually more, implemented right here. Right? So function is just uses SBO storage. Technically it's not specified like this, but most implementations use some size of SBO. They try to do this optimization. I think libc++ does 16 or 32 or something. And then in-place function is just a basic function with the right local storage. And the function view just has non-owning storage. And we could maybe even consider having shared function. I don't know, I don't care about it, but it's possible. And you're just using shared storage. So I think this way of seeing things as, behind basically a storage policy is pretty powerful, because function is just one example of type erased thingies, right? We also have polymorphic memory resource now, and they're using this nice base class interface, which I'm personally not a big fan of, but we could have maybe used something different for that, right? I can totally picture something like standard polymorphic allocator, which is just like standard function, except it doesn't require inheritance, and hence it does not make a bunch of choices and beforehand. So that's just an idea. Okay, so now we've talked about storage, and I said I wanted to treat storage and dynamic dispatching separately. So now we're going to only look at the dynamic dispatching. Are there any questions for the first part of the talk? Okay. So usually a vtable is remote. Regardless of the storage itself, you basically have a pointer to the vtable, and that's how you do your dynamic dispatching. But maybe we have some choices, right? What if we tried to actually inline the vtable in the object? That may or may not be very smart, but that's something we could do. So how would that work? Well, basically, you just need to take your v pointer and turn it into, I used to have a pointer to my vtable, and now I just have the vtable right there. I just skip the pointer. And now I've got all my vtable. Because I'm creating my vtable on my own, by hand, I have all my vtable in my object. And then when I initialize my object, I just have vtable, I copy my vtable from the static storage, and I store it in the object, and nothing else changes, basically. Well, I'm also not indirecting through a pointer when I do my virtual calls anymore. So it turns out this is, okay. So, and this is how you can do it with Dyno. So there's also a vtable policy. Basically, you can just say everything in my vtable has everything locally. It's a fancy little domain-specific language. If you're interested, you can go learn about it. But basically, there's a way of tweaking how your vtable is stored. And it turns out this is usually a pessimization, at least according to my not very precise micro benchmarks. Okay, well. Surprising. It's always a space pessimization. That's very clear because we have like the vtable in the object, so that takes more space. I don't really understand why it's actually slower, but so far it seems to be slower. I don't know. If someone knows why, go ahead.
I saw your Dyno code, and I think the reason why the local storage of the methods is slower is because you are hitting potentially cold cache lines as opposed to the vtable, which in any benchmark that I can think of is going to be very hot.
Okay, so that's possible. I don't need to repeat the questions, I guess, since they're on the mic. Okay, good. So that's possible. However, even when I hand roll it, so even if when I benchmark it with a hand rolled local vtable, like just the simplest struct, and I just put it there, it like without going through Dyno or anything, any kind of fancy abstraction, it's the same. I also see like it's so actually the same comment probably applies there.
Did you do the benchmark in the Intel platforms?
Yeah.
That's because the internal reordering of the buffers and the addresses, it doesn't really matter that you have an extra indirection if the indirection is already resolved. So you're not getting anything by storing it locally.
I see. Okay. Well, see, that's super interesting feedback. So I wasn't able to show that it was faster. So usually it seems to be a pessimization. Here's probably the explanation. And so again, the main guideline is always measure. However, something that may be possible is to just inline parts of your vtable, right? And basically the idea is, let's say you have a really hot, really hot function, then this one, maybe you want to pull it down one level, or maybe not, depending, I don't know. But if you do want to pull it down, then you could actually do that, where you have a part of your vtable locally in the object, right? So basically you just have a function pointer, or two function pointers, or however many you want. directly in the object, and then the rest for the other function for the other virtual functions like the destructor and stuff like that, which you don't care about so much, you can actually have a pointer to the v table for those. The way you could implement this is by having basically a v table that's the remote part of the v table, where it has like the destructor and whatever you don't care about. So the cold part there. And then you have a local part which has a pointer to the remote part and has whatever functions you care about. And the polymorphic wrapper would be a little more complicated, but basically it would reach sometimes in the remote part, sometimes in the local part. Okay. With Dino, you have this fancy little language that you can say, oh, my vtable, okay, only this function is going to be local, everything else is going to be remote. And so you can pick function by function which ones you want to have locally. And so here are some benchmarks. Calling a bunch of virtual calls. Again, I just cannot draw any conclusion from that, so I'm not going to even try to. So that's not super conclusive. So what I did was I looked at some assembly, and I asked a compiler engineer to decipher this for me. And what I got out of this, and again, some people in the audience may actually know more than many people in the audience probably know much more than me about this, but let's look at. So I have 3 different implementations. One is like a manual vtable that's remote. So I have my remote thingy, which has my remote any, which has a pointer to the vtable. And then I have my local any, which has the vtable right there in the object. And then for comparison, I have the basically an inheritance-based object like this. And then I just have functions that call these kind of virtual, or these functions that should go through the vtable. And I'm not going to do a super deep analysis of this because I'm just not able to. But what I was told is basically, okay, if you look at the, oh, I was on my screen. If you look at the remote one, okay, you'll see that there is basically 2 MOVs and then 2 moves and then a call, 2 moves and then a call, 2 moves and then a call, and that's it. And if you look at the, and it's the same for inheritance, right? You have 2 moves here, call, 2 moves here, call, 2 moves here, call. And if you look at the local one, the local version, there's 2 move and then a call, and then there's 1 move and a call, 1 move and a call. What is this? So here's what I was told. What I was told is one of these moves, the move that gets repeated every time with the remote any or the inheritance version, which are just the same. So this guy, move RBX, RAX, RBX, RAX, RBX, RAX. This is loading the V pointer. This is loading the V pointer into whatever is needed to call it. And then it's doing the call. And the reason why they need to do that is because when you do the virtual call, you're passing this, right? And you don't know whether you've modified something. The object would have changed. So they need to actually reload the vtable, the V pointer every time. Whereas if it's local, you see that it doesn't change. So you don't have to do that. Now, maybe none of this makes any difference in the grand scheme of things, but this is, I think, an interesting thing to know that optimizers need to, make sure that your code is correct. And sometimes when you hide what you're doing behind indirections, you know that you're never going to modify the temp V pointer, but they don't, right? And in order to be correct, they actually need to do that kind of stuff. And now I have another fun story about inlining. So I had this benchmark. I mean, it's not exactly this benchmark I had, but something like this, which instead of, I was type erasing an iterator there, which is not a super clever thing to do, but I was just playing around. And basically, I have an input vector and an output vector, and then I create iterators over my input vector and my output vector. And then I just copy the input vector into my output vector. And the interesting thing here is that each equals here, each comparison and each increment and each dereference is going through a virtual call because everything is type erased. Okay. And so I run this, And notice here, I'm creating my iterators through some make function, which is not inline. So I run this, and that's what I get. So the leftmost to your left is the static dispatch, where it's basically just a vector iterator. And this is a benchmark. I was probably not clever enough. The compiler was too clever. It probably just like elided everything, and basically it realized that nothing was going on, probably. Okay. And with inheritance or a remote vtable or like any sort of indirection, it couldn't figure it out anymore, and it had to do some work. Okay. And now I tried something, just a little tweak. I just did this. I just removed the no inline from the function that creates the iterator. So now the compiler was able to more easily see what function was being what iterator was being created. And suddenly, I got that. Suddenly, the Dino remote vtable was basically being, all the work was being completely elided. Why? And so what I think the reason is that inheritance goes like this. You have a pointer to a derived class which has a pointer to the vtable. With Dino or any fat pointer, that's how we call those, fat pointer approach, you have a pointer to the vtable which has some storage, in this case like remote storage, I think. And I believe that I was probably hitting some like some inlining limits in the optimizer, and when I made it non-inline, suddenly the Dino remote vtable, because it has one fewer hops, I guess the optimizer was seeing through it better, but it couldn't do that for the inheritance. That's my best guess at this, honestly. I'm not a compiler engineer, but I think the lesson is just that, hey, generally speaking, reducing pointer hops can lead to unexpected inlining, and when that happens, the gains could be crazy, And so in a real-world system, you may or may not have, a place where that could actually help. But if you do, you might be leaving lots of performance on the table. So it might be worth, trying to play around with. Yeah.
I think that it is not the reducing of the pointer hops what gives you the inlining, but value semantics. Because what is at the root of it all is that with normal C++ inheritance, you're always using referential semantics, and things can change in ways that are opaque to the compiler. If you do these benchmarks that I've seen your code, the compiler can see that something is a local variable, won't change, and therefore, even if there are many pointer hops, it knows that things are not changing because the activation chain is not opaque anymore.
I see. So that might even be a better explanation. Like I said, I'm not a compiler engineer, but so I guess then I should change this lesson to making your code less reference-based and more value-based, which is going to be helped actually by reducing pointer hops, basically. That can help the optimizer seeing through your code. And sometimes it can be pretty dramatic. So I think guidelines, by default, just don't bother with vtable inlining. It's probably not worth it. And it may actually not help. But you could consider inlining some methods if you know they're really hot, if you have some space in your object you don't care about, and if you've measured that it actually makes a difference, a positive difference. Otherwise, just don't bother. It's probably not worth it. But it's still an interesting thought experiment. So one of the biggest problems, I think, with what I've presented today is that it's super cumbersome, right? You have to do this boilerplate, and really nobody wants to do that. Nobody wants to deal with that. And the Dino library, I mean, let's be honest, it's cool what it achieves, but you don't want to be doing these compile time strings and all this weird domain-specific language. Nobody wants to do that in production code, unless it's super well hidden and everything. But still, but I think in the future we can actually get something much better. Say if we had reflection, I could take this struct vehicle and extract an interface from that, and then if I had something like code injection, my poly here could look at the interface for my vehicle and say, oh, I need to generate this method and that method, right? And then you wouldn't have any kind of boilerplate. You wouldn't need any boilerplate. We would just deduce everything. Or with meta classes, you could have this fancy interface keyword, right? Which I wish it wasn't based directly on inheritance, unlike super naive inheritance, but instead, we could actually easily make it based on type erasure, which is a technique that we've talked about today. That would be pretty easy. And so I think a summary for this talk, if there was one thing, or if there's a few things I would like you guys to remember, is that inheritance is just one way of implementing runtime polymorphism. We've talked about a bunch of them, and some of them may be better for some cases, worse for other cases. But it's absolutely not true that inheritance is a silver bullet, and that it's the only way of doing runtime polymorphism, which is usually what we assume when we do C++. I mean, currently I'm questioning the most fundamental thing in C++, right? This is what makes C++. It was C with classes. So what I'm saying is that's just one design choice, and it's not always the best one. Really not always the best one. It has many drawbacks. And you may not want to actually bake that choice, that specific design choice, in your program. And you can avoid doing this by using type erasure, basically creating your wrapper, your vehicle wrapper, and hiding how your polymorphism is implemented in that class. There's many ways of storing polymorphic objects. We looked at a few of those. It's always a space-time trade-off. The vtables can be inlined. It's not clear that it's a gain, but it may be. You just want to measure at this point, but it still is an interesting thought experiment, I think. And type erasure is really tedious to do manually, but reflection will be there to help. So the Dino library is available online. It's not like production quality at this point. This is still a little bit experimental, but you can look at it, and I'm welcoming of pull requests. Here's a bunch of links. The slides are going to be published, so you can go watch previous talks or read on the subject of type erasure. There's plenty of material out there. A bunch of people have worked on this problem before me. And that's it. Thank you very much. Yeah.
So you were saying don't bake this into your design. How would you, given the current state of C++ 17, recommend you not bake that into your design? So some kind of type erasure. You mentioned a few links.
Yeah, so you just use type erasure instead of using inheritance directly, basically.
What would that mean in practice?
What?
What would that mean in practice? So what kind of...
Well, I just showed like 4 different ways of implementing these vehicle wrappers, or you can use a library. And on these slides there's Adobe Poly you can use, there's Boost Type Erasure, there's Zach Lane's talk presents like a tool actually that can generate this thing for you. There's Eraser Face, which is a macro to generate these things for you. There's LibErasure, which you could also use. So like you have a bunch of
Yeah, so you're saying look at them all and take your pick.
Well, I would say use Dino. Honestly, I would say use Dino. It's more flexible than anything else I've seen, but it's kind of a little bit too experimental. But personally, I would say use Dino because it's simpler than what I've seen. But I mean, yeah, you take your pick basically.
Thank you.
Mm-hmm.
Hello. Okay. So there's a couple of axes that are really important to the performance discussion that weren't really touched on. So one of them was, we just talked about whether things were faster or slower to call, but there's a really big difference when you're talking about, I want to call one polymorphic object and I want that to go through as quickly as possible, versus I have an array or a vector of polymorphic objects and I want to call all of them as quickly as possible. Mm-hmm. For instance, the amount of space that it occupies, not very important in the first case, but very, very important in the second case, because the number of objects you can read in at once. And the second thing is that one of the reasons why storing the vtable remotely doesn't typically end up being a big deal, and I don't know if you tweak this parameter either, is that usually in the second case, when you have a huge array of objects, the number of classes you have is very small compared to the number of objects.
Everything's really hot, yeah.
What's that?
So like your vtables are basically really hot already, right?
Yeah, like your vtables will stay hot. So you have like 5 vtables and 1 million objects, and it's just not a big deal. And again, the win that you get from the space side of things almost always makes it worth it.
Yeah.
If you have 1 million objects and 1 million classes, then suddenly, if you think about it, like every vtable is new. Now you're basically talking about a linked list. Every single time you get a vtable, that's a cache miss every single time.
Sure.
So in that case, if the number of objects and the number of classes is the same, I would expect some of Dino's approaches to do better. But that's a very rare use case in real life, but it's not to say it never happens.
Yeah, yeah.
Just a couple of thoughts.
Yeah, no, that's good. I mean, again, I think the guideline clearly is don't do anything fancy with your vtables, just like leave them remote, right? And if really you have a fancy use case, then you can tweak it. It's easy. You just change a few lines, you try it out, and that's it. Yes.
Hey, so you might have touched on this, and maybe I just missed it, but with classical inheritance, you get the override keyword.
Hey, what?
Override?
Yeah.
So how does Dino solve that kind of contract? Like with override, you get you have to make sure that you have the virtual functions, or you'll get a compiler error, and that kind of stuff. So how does Dino solve that?
So there's no equivalent in Dino. I mean, you just have no inheritance at all. So there's no override or virtual keywords required at all. But yeah, you don't, which means that also like the classes that are supposed to satisfy an interface, they don't have a way of saying I want an error if I'm not, like, you just don't have an equivalent to the
Okay.
override.
So there's no way to enforce that kind of contract with
No.
Dino. Okay. Got it. Okay, thank you.
All right. So I really like the design you had with your basic function, where you have just a single interface with storage policy. Because one thing we do a lot in our project is just re-implement the entire std string with its 200-something methods, just because we want to control the small buffer optimization. Do you think it's a new direction the committee could take? If they have a new container, just define a container interface, offer a default storage, and let users choose the storage they want?
I think this would be something. Okay, so my personal opinion is that it would be useful to have a general way of customizing storage for people that need that have very tight requirements, like basically people on SG14, right? I think that would be useful. I believe the committee might not like this idea. I don't know. I just don't know. It's just my intuition is that maybe it would be seen as being too narrow or something.
Right. One problem I can think of is, for example, for std vector, if we could change the storage to use a small buffer optimization, you'd lose the guarantee of when you move the vector, the iterators might be invalidated if you don't have a remote storage. I think that could be a concern, is that
That's right, yeah.
the template has a different concept depending on the storage policy.
Yeah,
So.
yeah. I think that's also very true. I hadn't thought of that, but yeah. So there are definitely challenges to actually generalizing this to many, many more kind of containers or anything. So I don't know. I think it's an interesting. All of this is very experimental. It's like an exploration of what we can actually do. So I think it would be interesting to see what happens if we do it with containers. Maybe it flies, maybe it doesn't.
All right. Thank you.
Yeah, I'd like to raise a few concerns with inlining.
Sure.
As you might know, the modern compilers are sometimes capable of inlining the virtual calls.
Yeah, devirtualization, yeah.
Yeah, and I personally have faced the limitation, or actually a bug in the compiler, when the compiler decides to inline the call, and then I add a different runtime module and feed another object. And
yeah,
the bug is here.
Yeah, well.
So the inlining on virtual calls should be avoided, in my opinion.
I think that's between you and the compiler. I think that's between you and like if Clang does it and you don't like it, for example, you file a bug against them. I mean, I see your point, but I think for most people, the ability to do the virtualization far outweighs that kind of stuff. But anyway, like I don't really. What I think is just like, if it is a problem, then you should definitely talk to your.
If you can make sure that all the objects live inside a single module, and you compile this module, then the inlining is okay. But if your program consists of several modules and they do runtime linking, so one module can send an object to another in runtime, then this inlining kills your program.
So I mean, technically, if you wanted to avoid inlining, you could put like a no inline. I think you could probably do put like a no inline attribute, and I don't know exactly where, but there's a place where you could probably do like a no inline, because you have control over your vtable if you write it by hand or with Dino. So you could almost certainly make it go through a function call that's marked as no inline for your specific use case, and then you would know that this is never inlined, I think.
Okay, thank you.
Hey, since you mentioned Sean Parent's talk on polymorphism, what's your take on the concept T base T technique he shown, I don't know, maybe 2 or 3 years ago, I don't know if you remember it, because it looked a bit simpler to me, and maybe since it's usually actual polymorphism behind the scenes, the compiler is able to better optimize it.
So in all the benchmarks, so I'm aware of that technique actually. I decided in previous versions of the talk, this is the first thing that I showed, but based on feedback I've got from doing this talk at like meetups, I actually removed it because people would not understand it. So I had like to spend a lot of time to explain this one. So also in all the benchmarks that I've done, they're like, it's not better than the hand rolled ones. So I don't know.
Maybe if we improve that with some small buffer optimization.
It's not clear to me how you could do. You could probably do small buffer optimization even if you're using. Yeah, you could. Yeah, you could. I mean, Adobe Poly does that, right? They have the SBO. But like vanilla, the vanilla technique, the technique that Sean shows in his talks, if you just take it as is, it's no better than just,
All right.
And this is going to be the last one because we're out of time.
Hi. Since you're exploring the space, have you given any thought to open multi-methods?
I have. I think it's a difficult problem to solve. And I think, actually I've spoken to someone that that wanted to do this, to add this to Dino. I don't know where it's going to go. Yeah, I think I personally don't have the bandwidth to do that, but I think it's a really interesting problem to solve. It's a really difficult one, especially to do that efficiently, and it can almost certainly be solved. But yeah, there are no plans at the moment.
All right, thanks.
Okay, thank you, everyone.